Okay, this is the last stage in my guitar preamp. It's, other than the power supply, I guess we don't have a whole lot more to talk about. So basically, like I said, you get a little bit of signal loss each way, just from passive filtering and it's going from stage to stage. And I just have makeup gain at the end, and just a few speaker simulator too. But I guess I'll mention that. But let's talk about the amp first. Okay, here it is. There's an effects loop coming back into this. See, we've got a emitter follower. So this is basically like a low impedance signal. And if it weren't for that, we could build this a little different. But using the effects loop coming back in, I don't know exactly how, what the output impedance of the preceding stage in the effects loop is going to be. So I kind of make this, high enough to accept, I don't know, common signals. So let's, well, I'm going to copy this and we're going to sort of simplify it a little bit. Schematic. Okay, I'm going to take the speaker simulation out of it. It's kind of we can talk about that a little bit, but okay. So let's grab some power here. Okay, we'll grab some power. I'm gonna grab a signal. Okay. Let's hook the power up to here and put a signal on this. Now I mentioned that a signal, consumer level signal, is going to be like around, I think, 345 millivolts. Okay, I misspoke a little bit. I'm just kind of scanning through Google stuff. It looks like 316 millivolts. A few other places say that 316 millivolts consumer level audio, and that's kind of the working voltage. So, keep that in mind, and also keep in mind what's going on here. By the time it gets down here, and especially this, like, when you look at a guitar signal on an oscilloscope, it looks wildly, peaked at points, and it can be, but most of that peaking occurs like in the middle of your frequency spectrum, like around 2K or so. And these tone stacks have an obligatory mid-range cut that you can't get rid of, even if you turn the mid all the way up. So the signals get tamed down quite a bit before they get into here. It's not the situation you have here at the beginning of it, where you have to really worry about hot signals more. Saying that, you don't want to plan. You don't really want to plan for too much headroom, I don't think, because if you're really planning for all that headroom that you don't need, it takes the space out of the ability to amplify it. So, see, there's this trade-off between the input and the output voltage, and we'll talk about this more because there's so much about building amplifiers like this, these simple Class A amplifiers that people don't talk about, and I'm going to try and get to some of that because there's really a lot there. I'm going to I'm just going to break this down a little bit more actually. We're just going to simplify this for now and just look at it. It's a little weird, isn't it? Sorry. Okay. And just kind of look at a basic amplifier and talk about it. And I would say the first thing that I'm going to just try and talk about things that nobody seems to say but are necessary to know about. Like people forget about because they get into the algebra so much that they don't explain some really basic things. But the first thing that I'm going to talk about here, and I'm going to try and complement other videos because, you know, there are so many good videos on Class A amplifiers, so I don't really want to get into the stuff that everybody talks about. I want to talk about what people don't talk about. And the first thing I want to say about these Class A amps, and this is something that, like, I wish somebody had told me when I started this, and that's that like you have to split the voltage between output and input. And what do I mean by that? If you have 9 volts, okay, you have a total of 9 volts. You can give 3 of it to the input, and you have 6 left for the output, okay? So you can split it up however you want, but you have to split it into 2 separate parts. It's not like you can always have 4.5 volts peak to peak and have your output right in the middle because you have to have room for the input. Basically, it's just like I said. People don't say that, but it's very. We'll see if I can demonstrate that just by looking at this here. But let's just make this 0.5 volts amplitude. I'm just gonna get rid of some of this stuff. We'll leave the delay on 10K. We don't need the AC. Okay. Let's just not worry about this. I don't want to make things harder. So let's see what we got here. I'm gonna close out of this. Alright, so this kind of starts to illustrate what I'm talking about. And it's not, there may be, if even pen and paper might be better for this, but the point is, you've got like some space down here, and you've got some space up here for the signal, and they can't hit each other, and you only have so much space to place stuff in. So I'm going to see if I can there's a 9 volt there. There's 0 and there's 9. So you have to split this. You've got to split it into 2 different areas. And so I was trying to think if I can draw a line on here, something I really can't, but so let's say, well, I think you can see what I'm talking about. But I'm going to see if I can illustrate it a different way. Hold on just a second. Okay, so I'm going to give this a try. I've never tried this writing pad before, but I think I'll probably explain it a little bit better. So let's see, you got like, hold on a sec. Excuse me. Okay, I'm going to give this a try again. Like I said, I've never used this, but let's see. You've got like 9 volts, let's say. You got 0 volts. And that's all the space you have to work with. Like, here's your ceiling there. You got 0 volts here. And so in between it, you've got your input and output. And so your input has got to be like down here. Sorry about that. Ooh. All right, so your input is basically reserved for this, or output's reserved for this. You can't overlap. You only have so much voltage to work with, and the input and output are split. I mean, I don't know why people don't talk about that. They just get straight into the biasing and all the algebra and so forth, but this is a fact of the matter. So, like if this is reserved for this, and this is reserved for this, then you're going to set usually your input like halfway in between there and halfway in between there. So let me draw that and we'll pause. Okay, I drew that, and you can tell I'm not a graphic artist, that's for sure. But my point is, you've got this much space right here for input. You've got this much space for output. You're starting at 0 volts, 9 volts. So maybe you have like, I don't know, maybe 7 here and 2 there. Depends on how you do it. But, this right here is going to be, you call the bias. That's kind of the, it's what this line would be called. Same here, and this would be a bias because it's kind of what your signal rides along. Now the second thing about this, okay, this maybe wasn't intuitive when you thought about amplifiers, but there's something else, and I'm going to draw this or try and draw it. It's going to look a little bit weird, but it's kind of conceptually how I think of it. So I'm going to try and actually draw this and see if I can. It's kind of like mentally, this is kind of what I see when I'm working on this. First of all, let me kind of rearrange this just a little bit. I'll try and make this look kind of reasonable. It's going to be drawn in a funny way, but it's just, so I'm going to draw an actual transistor here. Sorry about my wonderful skills. Okay. I'm going to draw it like this. I'm going to do this. And we're going to go up here. We're going to go down here. Okay, back up for a second. I'm going to draw it with this pen because this is really what I'm trying to do. Excuse me. Okay. Oh, I messed it up. Excuse me. Should be that. Alright, we'll try it this way. That's a very bad looking resistor, but okay. Okay, and this is ground. Well, it looks terrible. Let me back that up and try it again. Okay, so this is terrible looking drawing, but I'm hoping that it illustrates what I want. You may say, oh, this guy's crazy. But honestly, like, this is what I kind of picture in my head, not this messy. But here's what you got. Here's the transistor, and I've tried to actually draw it on there. There's the emitter, the collector, and then the collector resistor and the emitter resistor. And this emitter needs to be right there. So like here's the voltage you have available for your input. Here's the voltage you have available for your output. And here's kind of where you put them. Now there's actually more nuance to this. I mean, usually you want some you might want some cushion between these, and maybe you want to settle this closer to the middle. I mean, there's all sorts of different ways to do it, but this is kind of the maximum scenario. I mean, you can't fit any more output or input into this. So this is kind of how I initially, well, how you can kind of visualize these two together. And Now the other thing is you've got like your different, let's see here, well, that's not working. Okay, then you've got another resistor here going to the base. This is, we're going to use kind of a standard type bias looking configuration there. I know this is terrible looking, but it's just what I'm going with right now. So you've got this is up to 9 volts. Of course, this is also ground. So you got this with a capacitor. Oh, and some input. So of course this is connected. So the reason I draw this on there, it's kind of not important for the output because that's really what we're thinking about. But the way you determine this point right here is you set this. And it's very easy because if you want this, like say you want, let's do a really specific example. Let's say you want to use 2 volts for your input. 1, 2, and then you want the rest for your output, which is 7. So you've got, we'll say like, 7 volts here, and you've got 2 volts here. Then the next thing you do is you say, well, then this has to be 2.7 because this is a voltage drop across the emitter. So this here is going to be 2.7. So then you set this voltage at 2.7 just with the voltage divider here. Then you only have one resistor left to figure out. But this is what I wanted to illustrate mainly here, is that you've only got so much voltage to work with, and you have to split it up between the output and the input. So we'll just leave it at that for now. You can see here, this just happens to be the amp that was with, in my amplifier, but you can see we've got this line set at like, what is that, like 0.9 volts. We've got this set at 5.6 volts. Now we said that its working voltage is like 316 RMS, and to get, you multiply by 1.4 to get the RMS value, which is 440. I'm sorry, that was the RMS value. This is the peak value. So that's going to be peak to peak. It's going to be double that. It's kind of 0.8. So this is kind of low. I mean, I think I probably should have given it more headroom. But on the other hand, we're not going to exceed it. I mean, I've scoped the signal actually and found that this was adequate, and because of the loss in the amplifier. So I sort of just experimentally looked at it and found that that should be fine. The clean signal coming back from the effects end could be louder than that, but it shouldn't. You wouldn't want to set it that way generally. You'd want to set it about the same level that's going out to it, which is, about in this range. So that's just how I did it. I mean, you can design this different ways. So so we've got this. Here's that, and here's this. Okay. Now, like the first thing that I wanted to mention that people don't talk about is this whole concept of splitting up your voltage from the input to the output. So let's say what else I want to say about this. Just kind of bring this stuff in a little bit. Okay. So it kind of goes without saying that when you're building an amp, you just have to know how much input's coming into it. I mean, to design it really, because otherwise you don't really know how to split that up into your input and output. The next thing that I usually look at is the input impedance. Okay, now there's different ways because you can build these different ways. So I'm saying like step number 1. So I'm just going to say here, I'm just going to like kind of keep track of this a little bit, but step number 1 is going to be how big of signal do I have? Input signal, that is. Now you don't always have to do this in this order, but this is the way it comes up for me most of the time. Is, you know, this would be the first thing I'm usually thinking of. The second thing I'm thinking of is what input impedance do I need, because I'm feeding something into it, and so I have to know, well, what is the input impedance of that I need? It's usually 10 times higher. So I'm just going to type this in, what input impedance do I need? And here's something else that, again, people don't really say, but it's depending on how you design them, this is usually true. So let's say I need, I don't know, say I need 100K input impedance. The way you're going to figure that out in most amplifiers is the following way. You look at this resistor here, the lower biasing resistor, and if you need 100K, you go one step up in the E series. Let me show you the E6 series, E12 actually. So these are your like 1K, 1.2K, 1.5. These are the different values you have. So if you need 100K, you go up to 120K, and we'll check. I'll show you why here soon. So you set this at 120K. We'll just kind of go through this here, and again, I'm going a little off track for my preamp, and I'm kind of showing you how you do this. So let's say we have we need, as in this example here that we drew out, we need a total of 2 volts, or like 1 volt. Now we expect our signal to fit in there and not hit or clip. So, but we're just going to set it. We'll say we have a signal that's going to be less than 2 volts peak to peak that we can place in there. So we're going to set this at 1 volt, which means we're going to set that at 1.7 volts. Okay, so you got this here. We already said that we need 100K input impedance, and this is kind of you'll just see how it works as we go, I believe, especially if you watch a few other videos. But the reason this works out this way, and I'll explain it ahead of time here, is that when you're looking at the input impedance coming in to this device, it splits this way, it splits this way to 9 volt, because AC sees the the 9 volts as a ground, at least as far as AC is concerned, and then you've got a third way that splits down here. And when you usually build these circuits, this is your lowest resistor. It offers the least impedance to the formula. So if you kind of step this up just one hair, so to speak, and then you fill these other ones in, when you parallel all three, you end up getting something that's around 100K in this case. That's where this is coming from. Now, the next resistor you can fill in is going to be right here. And how do you come up with that? Okay, so let me see if I can kind of fill this in. So you're going to want to step up 1 and make and fill in lower biasing resistor. Okay, so that's what you do there. Okay, we said we need 1.7 here, get 120K here. So basically we need to find a resistor so that this bias is at 1.7. So I mean, you can look up algebra on that. I'm just gonna guess. I mean, it's a voltage divider. I mean, you could do this many ways, but I'm just gonna kind of wing it here. Excuse me. And well, that's not too bad. See, 1.8. So if I have 60K, I'm just experimenting here. 1.6. So I'm going to go with that first guess. Now, how did I guess that? I mean, I guess I've worked on these a lot, but that's not the point. This is a simple voltage divider. Let me bring up. Just look at that voltage divider equation calculator. This is one I used to use. I actually use. You can see you've got voltage divider here. Just put an arbitrary thing. We said the lower one's 120 kilo ohms. Put in 470 kilo ohms. Output voltage is 0.2. Or that's different. What is that? Okay. Oh, whoops, I put in the wrong voltage. That's not 1 volt, that's 9 volt. You can see right here is a voltage divider, and here's the equation. Look up voltage divider equation, calculate 1.83. So that's good. That's going to bring us in a little higher than what we wanted, but I mean, it's better to be a little higher than a little lower. So so we've got this here. Let's see, I'll add that to the list here. Okay, calculate upper biasing resistor with, what we call that, voltage divider equation. So that's what we did there. We only have a couple left. Now, this is the next one I fill in. And here's how I fill it in. This, again, these are rules of thumb, but you can just make them fast without a lot of algebra if you get practice with this. Now, there's usually this ratio here. And the reason there's a ratio there is you want the current going through this to be 10 times more than the current going through the base, because that way, if the current here is small going this way compared to this one, it's not going to affect the bias. So as a rule of thumb, if you have a transistor with an HFE of 100, you can lower this by a factor of 10, which would make this 12K. So you'd put a 12K there. That's if you had an HFE of 100. Then if you say, well, obviously my transistor is more than HFE of 100, it's going to be at least 200, then you cut that in half. So a lot of times I'm doing this the opposite direction. So you see 120K there, you immediately want to put 12K in there, but then you can say, oh, I can do better than 12K. I'm just going to cut that in half. And a lot of times it's opposite. Like if you're building an emitter follower or something, you're kind of going this way to that way. But anyways, I mean, you can put 12K there. It's not, that would work, but it's unnecessarily high. You might as well go down to like 5.6K. And you'll see later, we'll check those currents going through here and there. So this is, you know, how you this, the next step then would be to divide lower biasing resistor by 10, then by 2. So what's that, by 20 actually? But I mean, I usually do it in my head. I just cut it down by a power of 10 and cut it in half. Just telling you how I do it. And that is your emitter resistor. Okay, and that's, you know, when using these standard E values, you know, right here. So the next thing you need to do is, you can do this by trial and error if you want. I do that frequently, but the next thing you have to do is you sort of look at the situation as a whole. First of all, let's mark this right here, and I'm gonna mark this. We know that this drops by 0.7, so I'm gonna mark this. Where we go? Yeah, it's right here. Sorry. I'm going to mark this with 1 volt. All right. Now it's sitting at 1 volt, but that's where this thing is riding along. Let's look at this bad picture again. It's 2 volts, the whole area or the whole range, but it's riding along 1 volt, right? Up and down there like that, because it's a sine wave. And well, that was bad. Anyways, you get the picture. This right here, the emitter follower, is at 1 volt, and it can take almost a 1 volt negative swing, almost up to 2 volts there. And so this one here, you've got 7 volts left. You can, I guess you could watch other videos for that, but basically you've got to use the ratio of 1 to 3.5 to get these resistors. So because this is sitting at 1, this is sitting at 3.5. So hold on just a second, we'll do that. Yeah, so I want to explain this a little bit more, you know, to explain at least my thought process. So we've got one more resistor to figure out, and in my mind, I've seen this so many times, and probably you have too. If you work with this at all, you'll probably know that there's a gain formula, and the gain is that if you take this resistor divided by this one, that's the gain, right? So if you look back here at our little drawing here, you've got the voltage is coming in. It's 2 volts peak to peak, and your output signal is going to be 7 volts total peak to peak, or 3.5, you know, on either side of this bias. So you can kind of do it either way, but you know, when you look at it, that just means that your gain that you need is going to be 7 divided by 2. Okay, so that's the gain that the maximum gain that this circuit can do, 3.5. So, you know, saying that, you got to go down to here to 5.6 that we chose, and then you're gonna 0.6 times 3.5, and we come out with 19.6. And so I'll just, even though that's not a common value, I guess I'll just put it in just to see how it comes out, and then we'll play with it after that. Okay, now we'll run this, but let's just check the biases first of all. Okay, this is it's a little bit higher than 1.1. That's kind of close. This bias is like at 5 volts. So let's kind of look back here. We were expecting this to be at 1, and then you add another one for 2, And then 2 plus 3.5 is 5.5. So that's what we're coming out with as far as our biases go. This is a little bit lower. This is a little bit higher than 1. This is a little bit lower than 5.5. It all started because this was a little bit too high. But you got to choose a value, right? So, I mean, I could alter this to get that right at 1 and try, but you know, we got to use real values here. So, if we do 22K, let's see what we got there, which is a real value. And we've got, it's being pushed down a little bit more to 4.5. You're going to lose headroom either way. I guess 18 is probably your closest value, and the gain is not going to be quite 3.5, but this kind of puts it in a little better area. So that's how you get your 4 resistors. Now, why is this? Let me plot the ground. Let's put 9 volts in the ground. So we've got this riding around 1, and this one's around 5.5. But you know, when you look at the signal here, this is the signal. We're only giving it 500 millivolts. We kind of planned it according to this ugly diagram. We planned it a maximum of 2 volts peak to peak. So let's just increase that and just see what it looks like. Amplitude of 1. This is going to be really cutting it close, but you know, I mean, these are sort of maximum calculations that we're doing. So here's 1 volt. We should see this copied to, you're riding along the around 1 volt. Your output is going to be right there, and it's like I said, it's the biasing's not perfect because these numbers aren't perfect, but it's not touching. Now, once they start to touch there, this is when you have a problem. You can get clipping a lot of different ways. If you put too big of a signal in here, it's going to hit the bottom. If you amplify it too much, it's gonna, these two are going to hit, or it's going to hit that clip. So let's see here. Let's say we just guess we can do it this way. Let's put a little bit hotter signal in, too hot, so we can just kind of watch it clip. Amplitude 1.4. Let's show you what's going on here. Okay. You've got these hitting and clipping. This is hitting the 9 volt clip. This is just clipping. You see, you just run out of room there. So this is basically how I usually set them up. You know, you start off with figuring out. Let me put this last one in. Sorry. Okay, I will put collector resistor equals gain times lower resistor, or let's say emitter resistor. So you just basically take this, multiply by the gain, and how much gain you can have is dependent on how much space you have. Like I said, if you have, this is going from 0 to 2 volts, that leaves you 7. 7 divided by 2 is 3.5. 3.5 multiplied by 5.6 gives you this 18. So, so this is, you know, this is a basic way I usually set them up. There's different ways to do this. I picked the most common way that just comes up for me. Like I said, I know I need to figure out how much signal is coming in. I've got to figure out what input impedance I need, which is going to be 10 times higher than the preceding stage. then I get both of those things. That gives me where I need to set this input bias. This will set your input impedance. Then you figure this out for this voltage divider, and you use the gain for there. So it's kind of, this is a procedure I go through mentally all the time. Now let's just test this. I mean, I said that it'd be 100K input impedance. Well, you can calculate it because this leg here is going to be 5.6K times the HFE. Well, that's going to be, let's see, 5,600 times, we'll just say 300 to be realistic, 1.7 megs. And that's going to get paralleled with 470K and 120K. So I'm going to get out my calculator that I built, and we'll say 1.7 megs, and that gets paralleled with 470, which I'm going to say is 0.47 megs, and that gives us 368K. I'm going to take that 368K, I'm going to parallel that with 120K. I'm going to calculate that, and that comes out to be 90. So this is a 90K input impedance. So we're a little lower than what I anticipated, but we're in the same ballpark. If you want, you can move. Let's say, well, we need it a little higher. You can budge this up a little bit. You can go to the next value there and the next value here, and that's gonna do the trick. But let me undo that, and let's just test this. Let's just see what it really comes out to, the input impedance, because we're here we go. Gonna do one of these deals. Look at the Bodie plot. 32, 16K. It's the same. What in the world? I think I didn't set the AC value. Yeah. There we go. All right, so divide by I V2. Well, these are wrong. Okay, there we go. So this is going to be the input impedance. Let's get rid of the phase, the plot phase, linear. Okay, so we've got 90K. So our calculations were right. This is from 90.1 to 90.7. This exaggerate on the small scale, so that comes out okay. Tell you what, let's do gain too. Here is the input. Well, you know what? I think this will work. It's not really AC, but let's see if it works. Because I don't have bypass like DC decoupling capacitors on it. We'll delete this one and zoom to fit. Yeah, no, I don't think that worked. But anyways, we can tell that the gain is right. I don't think we need to go through that. But anyhow, so this is sort of like basically how I usually build them. Now, that's kind of the standard part, right? This is just a way you build a Class A amplifier. Now, there are two tricks after this that I use all the time. And the first trick, let's say, is going to be bypass capacitor. And here's how I usually do it. And these two tricks, they're just indispensable to me. First of all, you take a capacitor and you bypass the emitter resistor, and let's say right now we have a gain of like what do we say, 3.5. If you want to be almost 10 times, let's say, then you'd have to lower this from 5.6K to 560. But you can actually just put in a 560 ohm resistor here, and the AC signal, it will see this paralleled with this, and this AC impedance is way higher than this. So you end up, when you parallel these two together, this is the one that's important, and this ends up being it. Now, this will blow this out of the water, because you're going to clip, because we're just about clipping and running maximum now. So you might use that if you said, oh goodness, I thought I was supposed to have a 2-volt signal. I only have a 200 millivolt signal. I have to redo all this. No. I'm just putting this on so we can see the AC signal. That doesn't need to. So I'm going to reduce this down to like, I don't know, just 0.1. Just a low level signal, but then we're going to amplify it by 35 instead of 3.5, and that's about what this should come out to. So let's see what happens there. I'm going to do this. Alrighty. So we got here's the input signal, here's the output signal. They're on top of each other right now. So that's way more amplified. Notice they're inverted, by the way. I never did mention that, but this is inverting amplifier. Let's look at it from a different perspective. Let's look at the copy of the signal that should be riding along that 1 volt area. Then let's look at the collector, and there it is. It's up there, and you can see it's way more amplified, right? So let's see here. So you can even put like a pot on here that goes from like whatever, from 0 to, if you make it so that it goes to 5 or 10 times this, then we turn up all the way, the circuit really doesn't see this too much, and you can bring it all the way down to pretty low. I usually make it like 5 times this one here, this trim pot. Usually is a trim pot. Make it about 5 times greater than there, and the circuit sees a little bit extra gain, but you can adjust it up and down. Now something happens when you do this, and it may not be obvious to somebody who's a novice, but when you look at okay, we mentioned that you find the input impedance here by paralleling this, and this resistance here. Well, when you bypass this, it changes the resistance across here. So if you get this too low, the input impedance will start dropping. And the way, again, how we said the input impedance, or the resistance across here, is going to be 5.6K times the HFE. But if you parallel it with something else, then you have to take into account this parallel. Now with this parallel resistance between here and here, you're basically left with the lower one because it's 10 times lower. So you end up getting something a little less than this. So if you take like 560 times, say, 300 HFE, then that's like 168K there. Well, that really starts to cut into this a little bit more. So, there's a balance here. It turns out that a lot of times you got to look at the design, but if you've got some good impedance matching here, and you start to lower it and you start to lose some signal, you have to ask yourself the question, well, yes, I'm losing signal from the impedance mismatch, but I'm also amplifying it more from here. And usually amplifying it typically wins. Like you usually amplify it more than the impedance you're losing. But if you get too low, it can just affect things negatively. So this is the first trick you can kind of use. And the second one is another one I do all the time, just very frequently. And so you've basically added 2 more pots where you can get a lot more gain out of this. Second thing you can do is use use 2 more parts and add a DC coupled emitter follower. And so let's just look at that. It's real easy. Okay. And let me just hook it up and we'll talk about it. Okay. Now, we've got an output coming to this base, and that signal gets copied right across there. And this is low impedance now, lower impedance, way lower, and it's 0.7 volts lower. I never marked what this is, but whatever this bias is here, it'll be 0.7 lower, thereabouts. So you can do this. You just add these 2 parts to your circuit and you're set. I mean, you can run this into the next stage. Because, one problem with these Class A amplifiers like this, these transistor simple circuits like this, is the output impedance can be kind of high comparatively to like op amps and stuff. So you can add these 2 parts and you're good to go. Now, how do you figure out what this is? Well, it's here. I'll just go through that. You've got, this is the output impedance of the amplifier. It's going into this next stage. So if this is 18K, so you need at least 180K here if you don't want any signal, or you don't want a lot of signal loss. So how do you get this to be 180K input impedance? Input into here, that is, the base. Well, you take 180K and you divide it by the HFE. So 180,000 divided by, let's just say, an HFE of 200 and be conservative, 900. So this needs to be 900, but we could make it like 1K. Now, so that would work. This would be great. You probably should, if you're like running off a battery or you want to save some, I don't know, energy, I guess, you can raise this up. You can even put it at 10K. The more you raise it, the more input impedance this is going to see. So 10K is like not bad because, I mentioned before, there's something to think about here. I'll just show it to you here. Let's make it easy. Okay, again, this my calculator. I always go to it. These are things I look at. But if you look at the current going across, see, the HFE is not really a constant. It depends on the current. Like if the current flowing across here is just really low, your HFE will start to drop off. And so you want it kind of in a sweet spot range ideally, and 10K is kind of at the lower end here. You won't usually want to go too much higher than that. Then you can go lower, to a point, but this is fine for most purposes. This 1K I use sometimes, 10K would be fine. I don't know, could make it 4.7K, but it's got to be at least 1, because you're going to need enough resistance at this base to go through. So enough on that. But So these two parts you can add bypassing here, and another way people do it, I don't like it this way as much, but if you want the same effect, you can like put one resistor here and one here, and then you just take this to a capacitor. Sometimes people will put a pot right here, and they'll put the capacitor on the wiper to sort of wipe it up and down, and that looks pretty cool. It works well for certain purposes. The reason I don't do that is because, I mean, it's not bad. I have done it before occasionally, but the problem with it is you can see how these precise values kind of matter somewhat. I mean, they don't have to be super precise, but if you put pots here, you're running DC through the pot, which it usually doesn't matter because it's not really high voltage or high current stuff, but a 10K pot might be like 8K or something, or I mean, they're rarely ever right. I mean, they're usually off by quite a bit, at least the ones I have. So I don't really trust the value of them, is why I usually don't do it. But a lot of people do. As I mentioned here before too, this is kind of this is another trick too. This is something I occasionally do with amps to sort of save a stage, like especially if you don't know what the output needs to be, you can kind of use this. You can put a pot here, and say if the pot was like a 1K pot, and you turn it halfway down, you cut the signal down, so you can kind of do that. Now this is a little bit different because you're not really the bias won't be affected really by this that much. It's already set right here, and then you drop it by 0.7, and it doesn't have to be as precise if you're using it on an emitter like that. And I know this is getting long, but this is like everything I know about about this practically, so I can't really say a whole lot more. You gotta watch these capacitors here. You have to say, well, how big of one do I need? This is 90K. I mean, there's a rule of thumb here, and that is that if you're, and this is for like general use, it's not like but if you're going into like a 10K, if you've got 10K input impedance you're going into, you need at least a 10 microfarad capacitor. If you're going to like 100K, you can drop down to 1. If you go into 1 meg, you can go down to 0.1. Those are kind of rules I use. Some people go higher than that on their capacitors because they don't want any loss at all. But I find that that works out pretty well for usually what I do. So that's what you're doing, is you're calculating a roll-off frequency basically. Here's my calculator again. But we said this was 90K. We're using a 1 microfarad capacitor. The roll-off frequency is 1.8 hertz. This is just an RC calculator basically. If anybody wants this, by the way, get a hold of me and I'll get it to you. I use this all the time. But so you're rolling off at 1.8 hertz. That's fine. If you went with 0.1 instead of it being 1.8 hertz, it'd be 18 hertz, which actually isn't too bad either for a lot of applications. So this is something to watch out for. You got to pick this right. This one here too, I'm not going to get into, but usually people use like 33 microfarad. I usually use 10 for most things. I mean, it actually depends on what you're bypassing. It's kind of a long it's not that hard, but I would just look that up if you need help, and if you can just always go a little large if you're not sure. There's something else that I think should be mentioned, and this is and it's like noise in these amplifiers and oscillations and feedback. Okay, here's what, long story short, here's what you usually should do in a lot of situations. You don't always need to do it, but basically you do the following. You just put a resistor here and a capacitor here. What happens is, like, say you have a bunch of different areas in your circuit where you have amplification occurring and so forth. Some of that starts like feeding back or getting into the rails, like the power supply system or whatever, and somehow it gets back to the amplifier. And if there's like something that's being amplified that gets back this way and then kind of creeps down this way and hits the base and then gets amplified again, you get these big feedback circuits where you can get these oscillations that just happen out of nowhere. And the way to get rid of that is you basically put like a filter here that just filters out any kind of like ripple or sine waves or whatever that try to get in, any kind of signal that tries to get in, and you kind of just use like a low pass filter. And basically what you're doing here is, and here's how you do the calculation. Basically, you got 9 volts here, and you built this system around 9 volts, and so you don't really want to lower this voltage very much, because if you do, then it makes it appear as if it has less than 9 volts here. So you got to make this resistance like substantially lower than these resistances. I'm just gonna make this 1 now. Obviously that's wrong, but we're just gonna look at the currents going through here, and we've got 270 microamps, almost. So most of we got 4.2 milliamps there. Because this is 1K actually. So I'll tell you what I'm going to do. I'm going to do this trickery. This is drawing so much current. I'm going to not bypass, since this isn't really amplifying, it's just kind of, if anything, there's basically no way to get to this base, I don't think, without going this way. So you don't always have to filter this, although you can. You could raise this up and include this, but this is more important, doing like the amplification stage. But we've got 210 microamps. So we're going to want this to be like 10 times lower than that, basically. And let's see here. So most of the current's going this way, which makes sense. And this is 18K. So I'm going to say that if we make this like 1/10 of that, let's say, then this should remain pretty close to 9 volts. I might be wrong. Let's check it out. Obviously this is at 9 volts. Okay, this is at 8.6 volts. So we've lost 0.4 volts. I'm going to say that's probably okay, but yeah, you can go a little lower. Go down to 1K. Okay, so now this circuit is seeing, remember we built it off 9 volts, but it's actually going to be like less. I mean, it's going to be, less than that. So let's make this go on for like a second so we can see what's going on there. Okay, so yeah, so this thing, this circuit is kind of not going to have a full 9 volts. It's going to have 8.8 volts. That's pretty close. Okay, how do you figure out what this is? Well, you go back to, it's a frequency cutoff it's cutoff frequency. You just do it that way. You got 1K, and say we want to roll it down to like maybe a hertz or something like that. Let's see what we got here. This is 159 hertz. 10. That's down to 15.9. 100. It's 1.59 hertz. It's not bad. You could leave it at 100. What I'm doing here is I'm calculating the cutoff frequency, and this way anything that's below that frequency gets kind of filtered out. And so you'd probably want at least 100. So you'd use like an electrolytic capacitor there, I suppose. And this would help filter out noise and prevent oscillations. So I think I mentioned in another video, you can. I usually use a little series resistor there of some sort. Honestly, this should be like. I'll just make it more realistic. I wouldn't really use 1K there usually. So this is kind of the design you can use. There's one other trick, I'm just going to mention it, but I'm not really going to talk about it, is you can feed back. You can use this bootstrapping to feed back and make this higher impedance, and you can also put a Darlington here, but you lose some of the space available for your input and output signals. So I know that was super long-winded, but honestly that's basically all I know about using this is like 90% of what I know for sure. I'm trying to think if there's any other tricks or anything I can mention about this. I mean, more advanced stuff, like you can bypass this, but you can actually bypass the collector too if you want to lower the gain. You can do some neat stuff with that. You can feed back this emitter to get higher input resistances. I think I did that before. One thing you can do is like you can kind of sometimes there's usually enough room in here that you can maybe throw in some filtering if you have to, as long as you have a resistor across here. Sometimes you can do like, if you want, this is like 18K, you can put a little treble bleed capacitor here and make it at whatever value is appropriate. Like if you go say 18K and look at this, and we're going to set this really low. This is 18. Okay, this is probably, I'm calculating a cutoff frequency 47. Okay, that's probably, okay, this is a cutoff frequency of so that's 180. That's not right. Let's see. I want to go. Okay, sorry about that. Yeah, so you got 18K there, and you got this capacitor. If you want to make like a little bit of a treble roll off here, you can do that by just putting a little capacitor across here. And I figured it out here for 18K, which is the source. Output impedance. It's like having a series one across here, really. It's like having it in series with here. You could put this off, and that can kind of roll off some of those highs that may end up oscillating, or you can just use it as a filter. I've done that before. Anytime you have a lot of room between stages, you can try and figure out what to do with it. You can kind of, a lot of times these stages, like you can pull more than one signal off of them. There's just a lot you can do, but this I think shows there's probably a few other things, like you can do some AC decoupling, they call it, where you get more gain out of this. There's like different things you can do with this, but honestly, this is kind of a configuration I use a lot, and these are the steps I usually come through to arrive at what I need. That's probably enough, and I appreciate you watching such a long video. If you're smart, you probably watch it on 3 times speed. But if you have any comments or questions or anything, just please let me know. Appreciate you watching. I have one more video on this preamp, and then I think I'll take a break. Thanks for watching.